In this video revision lesson, we are going to continue answering some past exam questions. As I said, this is paper 2, structured questions. Paper 2 is divided into 3 sections: physical, inorganic, and organic chemistry. We started with organic chemistry. We are still continuing with organic chemistry section. That is section C. This is the 6th question. So now we will be answering question number 6. This is June 2020. Once more, I really want to appreciate those of you who have taken time to comment and subscribe to our channel. Thank you for a job well done. For those of you who haven't subscribed to our channel, please take time to subscribe to this channel, like our video, and share to fellow learners. Thank you for taking your time to do that. Once again, we are continuing with answering paper 2 question. We are starting with question number 6. It has to do with synthetic pathways. Now, the question reads: study the reaction pathways below from which compound P may be prepared from ethane, and answer the questions that follow. We have ethane. Once more, I apologize for the poor quality of the question paper. We have ethane. It is passed through bromine in UV light. We have bromoethane. So we have 1 to form M. We have 2 to form propanoic acid. We have then passed through a UV light again, that is a chlorination through UV light to have N. Then N, step number 3, to form P. And P is a 2-hydroxyl propanoic acid. Now 4, that is bromoethane halogenalkane to ethanol. Then we pass through acidified potassium or sodium dichromate. We will have O, and from O we have 5 sodium cyanate in dilute sulfuric acid. We will have the compound 2-hydroxyl propane nitrile. Then back to 2-hydroxyl propanoic acid. This is a synthetic pathway. You know, in this type of question, you should know, you must have studied halogenalkanes, how you can convert halogenalkanes to alcohols, how you can convert halogenalkanes right down to acids, the type of reaction that is occurring, a substitution reaction. And if it is a substitution reaction, is it a nucleophilic substitution? Of course, there will be a nucleophilic substitution. Now, taking it, you will see it. if you have watched our previous video on this type of synthetic pathways, you will understand more. But as we'll be going ahead, you will see them better. So now the questions, the question here says, A, give the reagent and the reaction condition for the conversion of 1. For the conversions 1. Conversion 1 is the halogenoalkane to M. The halogenoalkane to M. Now, the halogen, that is bromoethane to M. And bromoethane, what can you do with bromoethane to convert it to M? And from M, how can we get acid, a corresponding acid from M? Now, if you notice from bromoethane to the acid, propanoic acid, there is an increase in 1 carbon atom. And there is an important organic reaction that will help to increase the number of carbon atoms. And by doing that, we will have to use the cyanide ion. We will have to substitute it with cyanide. In that case, we will be reacting substitution with a cyanide, which is from hydrogen cyanide. And that is usually got by reacting sodium with dilute acid, because sodium cyanide or potassium cyanide is toxic. So you have to react with acid. By reacting with acid, acid will provide a proton that will combine with the cyanide to form hydrogen cyanide. And it's from the hydrogen cyanide that we can have our cyanide. Cyanide is Cn. The Cn is the one that when we attach now, that the Cn is used as a nucleophile. That nucleophile will help to substitute our halogen, which is bromine. When it substitute it, this is the cyanide. The cyanide, when we substitute, when it substitute the bromine, there is an increase in a carbon atom. And that carbon atom, when there is an increase in carbon atom, these can be hydrolyzed. Acid hydrolysis, it can be hydrolyzed to a corresponding acid. So let's go ahead before that. So in this case, in this situation, we have to convert bromoethane to M. To convert bromoethane to M, what is the reagent to convert bromoethane to N? Now, bromoethane, that is bromoethane, that is a CH3, CH2Br. We have to do it so that we can have an organic compound. And by doing that, we will have, when we react potassium cyanide in ethanol, when we react potassium cyanide in ethanol, we call it ethanolic solution of potassium cyanide. Reacting potassium cyanide in ethanol, because potassium cyanide is very toxic. So potassium cyanide in ethanol, when we react potassium cyanide in ethanol, or you can call it ethanolic solution of potassium cyanide, this is going to be released. A cyanide is going to be released, and this is going to act as a nucleophile. This nucleophile will come here to substitute this, and we will have a CH, a 3CH2Cn. Now we have 3 carbon atoms. The 3 carbon atoms here will be the 3 carbon atoms is the one here. Then we can hydrolyze this. Acid hydrolysis, hydrolyzing it with dilute acid will convert this to corresponding carboxylic acid, which we will call it CH3, CH2. This one again will convert this C to COOH. That's why it comes here. So in our question here, our reagent, go back please and watch our previous video on carbonyl groups, reaction in carbonyl groups. Now, our reagent in this case, reagent for one here, to convert this one, reagent 1 here, the reagent is reagent 1 and reaction condition. Reagent 1, for the reagent here, we will have ethanolic solution of potassium cyanide. We call it ethanolic, or potassium cyanide in ethanol. Ethanolic solution of potassium cyanide. Then the condition, what are the conditions? The condition, ethanolic, I say potassium cyanide in ethanol. Chemists call it ethanolic solution. So we can say reaction mixture is heated under reflux. Reaction mixture is heated. Is heated under reflux. Is heated under reflux with what? With bromoethane, with C2H5 here. Bromoethane. That's a condition. That is the condition. And now, what is the reaction? The reaction condition. I have said the reagent is ethanolic, because this is the one that is going to change the whole thing. Potassium cyanide. Ethanolic solution of potassium cyanide, or you can say potassium cyanide in ethanol. That's the reagent. Ethanolic solution of potassium cyanide. And the condition, go on the column of the question paper and write reaction mixture, that is heat under reflux with this. Heat under reflux. Heat under reflux with bromoethane. Okay, it takes us to the second part of it. 2. 2 here is we will have M. How can we convert M to acid? Okay, 2. I tell you that now 2 has now we are leading to 2. There is an increase in the carbon chain. So now 2. In 2 here, this has resulted in a compound. By doing this here, this will result in this compound here. It will result in, it's going to result in propane nitrile. That will be CH3, CH2, propane nitrile. Is it going to result in propane nitrile? That's going to be the result of our this thing. Where now we will now substitute it. This will now be hydrolyzed, acid hydrolysis. It's going to result in this. Okay, 2. 2 is the reagent and the reaction condition. Now we have propane nitrile. We now have this. We now have propane nitrile. How can we now convert propane nitrile to what? To the acid. That is 2. To convert it to acid, I said to convert this to acid, to convert propane nitrile. Propane nitrile is supposed to be M. This is supposed to be M. When we react By reacting this this with this, it gives us this. So this is supposed to be our M. This is supposed to be our M. Now, how can we convert our M to our acid? Now, our reagent now will be what? Our reagent here will be the nitrile to acid reagent. To convert the nitrile to acid, our reagent is dilute hydrochloric acid. Dilute HCl. Dilute hydrochloric acid. Dilute hydrochloric acid is used for that. Then, the condition here will be what? The condition for this is what? You will see how to do it, heat under reflux. The condition is heat under reflux. So now this is acid hydrolysis. You are hydrolyzing this. You are hydrolyzing this one because this one will be converted to what? It will be converted to CH3, CH2, COOH. So you will have to hydrolyze this using dilute acid to have this. Okay, now heat under reflux. And heating under reflux, we say it is hydrolysis of nitrile. Because this compound here is not an amine, it is a nitrile. There's 1, 2, 3, propane. We call it 1, 2, 3. That's propane nitrile. This is a nitrile. This, we will hydrolyze the nitrile. We will hydrolyze the nitrile by heating it under reflux with dilute acid. So now, I said heat under reflux. Hydrolysis. Hydrolysis of nitrile. Hydrolysis of nitrile by refluxing. By refluxing with dilute hydrochloric acid. So heat under reflux, that is hydrolysis of nitrile. We are hydrolyzing this nitrile. We are adding water to it to result in this acid. We add water to this, will result in this acid. Hydrolysis of the nitrile by refluxing with dilute acid. Okay. Now, when we do that, we will have this compound here. When we do that, we will have this compound here. Now, that compound there, now again, does what? It is passed through, it is chlorinated or halogenated with chlorine. The condition is what? Under UV light. And under UV light, what happens? It is only a substitution reaction that will occur under a UV light. So it will not touch the acid, it will touch by the alkyl group section of it. So it will start substituting the hydrogens. So it is a substitution reaction or halogenation reaction or chlorination reaction under UV light. UV light acts as a catalyst. So we will now start the substitution on this. We will now start the substitution by substituting from here. The substitution will start from here. So now, in substituting it, we will have a CH3. We will have, so it is a CH3, a CH2, a CN, a COOH. The substitution will start here. The substitution will start here. The substitution will start here by substituting the hydrogen atom. Now, if we substitute one hydrogen atom here, we will have, with chlorine, we will have CH3. We will have CH3, CH, but with a chlorine, one chlorine has been substituted. Then the acid comes in again. That is we have substituted. That is a substitution reaction. Now, it will undergo a type of reaction that a further substitution now will occur with what? As we will form this compound. We will form this compound. This compound, it is this compound, we will call it N. This is N. We call this compound N. This is compound N that has been formed. This compound N will undergo a type of reaction to form what we call P. And something here, P is what? P is a 2-hydroxyl propanoic acid. So something is done here by substituting this into an OH group. After forming this compound N, something is done here to substitute chlorine with a hydroxyl group. And what that is the condition they are asking us to give now. What condition is required for the substitution of this compound N? For the substitution of this compound N, you might not know the compound, but this is N. That is the compound. After substituting this, we will have a compound N, which is 2-chloropropanoic acid. Is 2-chloropropanoic acid, which is N. Then there is another substitution reaction. There is still another substitution reaction that will occur here in the 3 to give our 2-hydroxyl propanoic acid. And that is the condition they are asking us. So now, what is required to give us? What do you think? What substance, what reagent will provide an OH? What reagent will provide an OH that will substitute this chlorine to give us 2-hydroxyl propanoic acid, to give us this one here, CH3, CH, OH, COOH. What reagent will provide this that will substitute the chlorine to give this? In that case, it must be an alkaline solution. A strong alkaline solution like sodium hydroxide will provide that. So we now say that we can now say that our reagent okay. We can now say here now 3 reagent and the condition. Our reagent that is required here, I said it is 2-chloro, I said it is 2-chloropropanoic acid. So to substitute the 2-chloro here, our reagent here that will provide us a hydroxyl group will be what? Our agent will be aqueous sodium hydroxide. So our reagent is aqueous sodium hydroxide. Aqueous sodium. That is our reagent. This reagent will provide an OH group that will substitute the 2-chloropropanoic acid to give us this. Then the condition is what? The condition here is we need to heat under reflux again. We will have to heat under reflux. So now that is the condition for 3. Then number 4. And number 4 here is, we go back 4, looking at the synthetic road here for 4. 4 here, this is halogenoalkane. This is bromoethane. How can we convert bromoethane to ethanol? It is still a substitution reaction. So in that case, there is a reaction. We will need, again, aqueous solution of sodium hydroxide again for aqueous sodium hydroxide, aqueous solution of sodium hydroxide. And again, we will heat under reflux. We will heat under reflux. When we do this, we will heat under reflux, and what we will have will be our ethanol. Our ethanol. Aqueous solution of sodium hydroxide, and heated under reflux. We will have this one here too. Then again, it takes us to the other part. Give the names of the compound M, O, and P. You were very vigilant when I was saying M. I said M is to convert. M is when you have ethanolic solution of potassium hydroxide, potassium cyanide. Ethanolic solution of potassium cyanide, when heated under reflux with bromoethane, the result is the cyanide will substitute the bromine, and it will be CH3, CH2, CN. And we call this propane, because we call it propane nitride because there are 3 carbon. 1, 2, 3. Important thing with this reaction is it leads to the addition of 1 extra carbon atom here. So the compound name is propane nitrile. So now we say our M is propane nitrile. Propane nitrile. Name is M is propane nitrile. M is propane nitrile. Propane nitrile. Propane nitrile is a nitrile. Then O. Compound O is propane nitrile. This is O. Now we have ethanol. When we were in our previous video, when we were talking of reaction of ethanol, we said reaction of alcohols. We said alcohols will undergo oxidation. A suitable oxidizing agent for it is acidified potassium dichromate. Acidified potassium dichromate. This is acidified potassium dichromate. Dichromate 6. So this is a primary alcohol. A primary alcohol is oxidized. A primary alcohol is oxidized to what? It is oxidized to ethanol, to aldehydes. If it is not distilled off immediately, it is further oxidized to what? To the corresponding acid. So this compound could easily be oxidized directly to ethanoic acid. But because there is another substitution here, this one will undergo a substitution here. For that reason, it is oxidized but to ethanol. It is oxidized but to ethanol. Further oxidation is not required here. It is oxidized to ethanol. Then ethanol will undergo this reaction here with cyanide. It will undergo this reaction here with cyanide. And the reaction here with cyanide is nucleophilic addition. Go back to our reaction of carbonyl compounds, reaction of aldehydes. Nucleophilic substitution reaction with aldehydes. Nucleophilic addition reaction with aldehydes. So letter O will the compound O will be an ethanol. It is not oxidized to acid. It is ethanol, because that ethanol again will undergo what we call addition. It will go what we call addition, a nucleophilic addition with a cyanide. To form what? to form a compound that has a 4 functional group. Here you can see it here like this. This is aldehyde. It is this compound. We will have CH3. OH. This ethanol. Now, when it is oxidized to ethanol. It is oxidized to ethanol. Then it is oxidized to ethanol. Then it will undergo based on the with potassium cyanide. With potassium cyanide. Here, sodium cyanide in dilute acid. We will not use sodium cyanide because it is toxic. So there is a reaction with sodium cyanide will react with dilute acid to form hydrogen cyanide. It is nucleophilic addition with hydrogen cyanide. It now react with hydrogen cyanide. In that case, it now react with hydrogen cyanide. Which will be hydrogen cyanide will give this. Now, the hydrogen cyanide will give this because of the partial positive charge here. We will have partial negative and partial positive. Here, because of this one here, a lone pair of electron here. There will be nucleophilic addition here. Because of this is a nucleophile, there will be an attack here. And this will result in this compound which will have CH3 . It will result in this. You will see it will result in this compound. That will result in that compound there. Okay, sorry. It will result in a chiral compound, a compound with three different groups. So this is how it will result. So we have that compound. If you look at it, we have 1, 2, 3. There are 3 carbon atoms there because of what addition of the cyanide. So we now say it is 2-hydroxyl propane nitride. Here, this is 1, 2, 3. So we can say it is 2-hydroxyl propane nitride that will result as a result of this one. This one is going to act as a nucleophile to provide a nucleophile, a proton electron pair donor to provide a lone pair to this carbon here. And if it comes here, what happens? The lone pair here goes here. The lone pair of electron goes here, and there will be a negative charge here. That will be a complex. So that would finally result in this one. Now, in that case, it takes us to what we're saying, that the compound O will be ethanol. I said it will be ethanol because it's not acid. So the compound O will oxidation using acidified potassium dichromate to ethanol. So now our answer for this is ethanol. Our answer is ethanol. So compound O is ethanol. Then compound P, oh, I've just wiped it off. Compound P, I say it is 2-hydroxypropane nitrile. 2-hydroxypropane nitrile, as I just mentioned it there. P here is, B is P here. B is the first carbon, second carbon, and the third carbon. We now say it is 2-hydroxy, it is the compound here, sorry. 2-hydroxypropane nitrile. Now, 2-hydroxypropane nitrile undergoes what we call it is, because I said a nitrile is hydrolyzed. Acid hydrolysis to give out a corresponding acid. It's the same thing that happened here with N here. So it is now hydrolyzed to acid. To hydrolyze to acid using aqueous sodium hydroxide. Hydrolyzed to acid using dilute acid. So in that case, dilute hydrochloric acid. In that case, P is 2-hydroxyl. P is 2-hydroxyl. Propanoic acid. It is hydrolyzed to the corresponding acid. We call it 2-hydroxypropanoic acid. I showed a diagram here that it is, this acid has 4 different functional groups, resulting in a chiral carbon atom. So, name the type of organic reaction in step 1. As I explained, I said substitution in 1. In 1 here, there was a substitution. A cyanide is used to substitute the bromine. And this cyanide is acting as a nucleophile by providing a lone pair of electrons. So in that case, as a nucleophile. So it is nucleophilic substitution. We call it nucleophilic substitution. In 1, we say it is nucleophilic substitution. Nucleophilic substitution. Nucleophilic substitution with the cyanide ion. Nucleophilic substitution with a Cn- ion, cyanide ions. That is what is happening in 1. Name the type of organic reaction in step 5. Step 5 here, I said, step 5 here, sodium cyanide is toxic. So we must react sodium cyanide with dilute hydrochloric acid. A dilute sulfuric acid. When we react this, it reduces the toxicity, and the product from this reaction is hydrogen cyanide, because acid will provide the proton that will join with Cn to form hydrogen cyanide. So it is the hydrogen cyanide. Now the cyanide will be used as a nucleophile to add on to the ethanol that results from here. So in that case, it is an addition reaction. In that case, it is an addition reaction. Why addition reaction? Because the cyanide will add to the ethanol. Ethanol is only 2 carbon. When the cyanide adds to ethanol, there is an increase in a carbon chain. There is an increase in 1 carbon atom. So it is an addition reaction. But the cyanide is a nucleophile. We now say the reaction is nucleophilic addition with hydrogen cyanide. Nucleophilic addition. Nucleophilic addition with hydrogen cyanide. With hydrogen cyanide. I say, remember, hydrogen cyanide is produced when sodium cyanide, hydrogen cyanide is produced. Hydrogen cyanide is produced when sodium cyanide and dilute sulfuric acid react. A proton from sulfuric acid will add to the cyanide to form hydrogen cyanide. We cannot use sodium cyanide directly because it is toxic. So we call it nucleophilic addition with hydrogen cyanide. It's hydrogen cyanide. So in solution, the hydrogen cyanide will dissociate to give only the cyanide that will add to it. Okay. So that is the that is the type of reaction. Nucleophilic substitution for 1, and for 5, it is nucleophilic addition. Now, C part of it, the C part of it tells us on, by means of a chemical test, how would you distinguish the following pairs of compound, state reagent, and the reaction conditions? You know that these are all carbonyl compounds. Carbonyl compounds, they have the carbonyl group, propanol and the propanone, they all have the carbonyl group. And there is a particular reagent. If you have been watching our previous video, you will see how we can differentiate between, how we can identify that this compound is a carbonyl compound. There's a reagent we usually use for that. Then there's another reagent we will use to differentiate between the different classes of carbonyl compound. For the purpose of revision, we will use 2,4-dinitrophenyl hydrazine to show that a compound contains a carbonyl group. Then we will use toluene reagent to differentiate between aldehydes and ketones. So our answer here is the chemical test to distinguish between propanol, that is an aldehyde, and propanone, that is a ketone. The chemical test here will be what? A Siva-Miro test. Siva-Miro test. The chemical test is Siva-Miro test. State reagent and reaction condition. Here is a Siva-Miro test. We can say reagent here, reagent. 1, reagent. The test here is Siva-Miro test. Siva-Miro. The Siva-Miro test. Then the reagent. Our reagent here is toluene reagent. Our reagent here is toluene reagent. And our reaction condition is heat condition. Heat in a water bath. You have to heat in a water bath. Now, in describing it, you can now say with propanol, after warming the mixture with a sieve, after warming the mixture, how to describe, you can say with propanol, after heating or warming the mixture A silver mirror is formed in the inside of the test tube. With propanol, after heating the reaction mixture, there are two test tubes. Test tube A contains propanol, and test tube B contains propanone. So, with propanol, after heating the reaction mixture, a silver mirror is formed in the inside of the test tube, indicating that propanol is oxidized to propanoic acid and silver is reduced. So it's a simple thing, but with propanone, propanone, there is no reaction. That's just all. Since it requires just a few, the amount of material you give will depend on the space provided. The test is a silver mirror test. The reagent is stolen reagent. The condition is heat in a water bath. You can state now briefly with ethanol. A silver mirror is formed in the inside of the test tube, but with propanone there is no reaction. Full stop. You can go to the next one is ethene and ethine. Ethene and ethine. The test you can use here is ammoniacal solution of copper 1 chloride. You can use for ethine. You can use the test. There are two tests you can use. Test 1. Test 1 you can use ammoniacal. Ammoniacal solution of copper. Ammoniacal solution of copper 1 is copper 1. Copper 1 chloride. Ammoniacal solution of copper 1 chloride. Then test 2. There's another one. If you don't use that one, you can still use test 2. Test 2. Test 2 is you can still use ammoniacal solution of silver nitrate. Ammoniacal solution of silver nitrate. You can use any of these to differentiate between ethene and ethine. You can use the first one. Ammoniacal solution of copper 1 chloride. How can you use this one? That's test 1. Here you can say with ammoniacal solution of copper 1 chloride, ethine forms a red precipitate. Ethine. I said ethine. Ethine with this one, ethine forms a red precipitate. With ammoniacal solution of copper 1 chloride, ethine will form a red precipitate, whereas ethene does not. Then, if you use test 2, ammoniacal solution of silver nitrate, you can now say with ammoniacal solution of silver nitrate, you can say ethine. Again, ethine forms a white precipitate with ammoniacal solution of silver nitrate. Ethine forms a white precipitate. Ethine forms white precipitate with this. With the ammoniacal solution of silver nitrate, ethine forms white precipitate, but ethene does not. That's just all. So there are two solutions, as I said, ammoniacal solution of copper 1 chloride. With ammoniacal solution of copper 1 chloride, I am saying that ethyne forms a red precipitate with ammoniacal solution of copper 1 chloride, whereas ethene does not. If you decide to use test 2, which is ammoniacal solution of silver nitrate, you can now say that with ammoniacal solution of silver nitrate, ethyne will form a white precipitate. Ethyne will form white precipitate, but ethene, whereas ethene does not. That is just all. Now again, it takes us to the other section of it. Outline the mechanism for the conversion of benzene to methyl benzene. If you had watched our video on alkylation of benzene, you will notice that with alkylation of benzene, it is possible to produce methyl benzene. But here you have been asked to outline the mechanism. Outline means you don't have to go into details. You don't have to go into the details. So outline the mechanism for the conversion of benzene to methyl benzene. It's a summary. You are giving it a summary form of it. You are not going to detail. But I will give you, for purpose of revision, I will give you the details, then the summary that you are expected to give. So the first step in this, if you have watched our previous video, the first step in this is step number 1 for the conversion of benzene to methyl benzene. Step number one, generation of a carbocation electrolyte. Generation of a carbocation electrolyte. Generation of a carbocation electrophile, sorry. Generation of a carbocation electrophile from chloromethane. From chloromethane. Here, what you usually do here is this. You will have your chloromethane. This is CH3. This is CH3. Remember, there is acid. There is a catalyst. The catalyst is aluminum chloride. There is a catalyst here. And I told you there is a coordinate bond between the catalyst and this. So what happened here is there is here you can put it like this for you to better see it. You have it in this form. Let me say it is H3, so that you see the polarity very well. This is positive and this is negative. So what happened here is there is the generation movement of. There is a heterolytic fission here. Chlorine is more electronegative. It takes the bonding pair of electrons. So what happens? The bonding pair of electrons will be used to attach to the catalyst here, aluminum chloride. And now when there's heterolytic fission, a breakage here, the electrophile is generated, and that results in this electrophile. It results in H3 D is the electrophile plus the catalyst. D is the catalyst here. Yeah, the catalyst. That is the catalyst. Step number 2, that is step 1. Step 2, in step 2, the carbocation, this is the carbocation, we call it the carbocation electrophile. This is the carbocation. The carbocation electrophile. Step number 2, in step number 2, what happened? The carbocation electrophile is attracted to the delocalized electron system. It is attracted to the delocalized electron system. Carbocation attracted, or can say electrophile, attracted or attacks the benzyl ring. You can say attracted to the delocalized electron system. Electrophile attracted or attacks the delocalized electron system, distorting the ring. Distorting the ring. Distorting the ring or the localized electron system. And this is what will happen there. Here, this is what you are going to observe. This is what you are going to observe there. You will see this is the electron. This is the electrophile. This is the carbocation electrophile. This is the distortion of the ring. The ring has been distorted. Here, what is happening here is, I said electrophile, the electrophile is attracted or attacks the benzyl ring, therefore distorting it. Now, this electrophile is highly reactive. It needs electron to bond itself because the 2 electrons were taken away by chlorine. So what happened is that the delocalized electron system here, they will use 2 electrons from the delocalized electron system to form a bond with this one. And when the 2 electrons are used, now the ring will be distorted, the ring will be partially broken, and this results in it because it has attacked itself here. It gets to the last step where the hydrogen will now live as a proton or a hydrogen ion, while the methyl group firmly attaches itself here. Step number 3. Step 3. Step 3. Can say step 3 is what? Hydrogen is expelled from the ring. Hydrogen ion is expelled from the ring. Hydrogen ion is expelled from the ring. by aluminum so now so finally you will see that the final step will be so in that case we have this. So now what is happening here is that this hydrogen will leave as a hydrogen ion and will attach itself. Then there will be a breakage here. There will be a breakage here. And the lone pair that this chlorine is going to go with will be donated to this hydrogen that is leaving as a hydrogen ion to form hydrogen chloride. And now what happens when hydrogen leaves as an ion, the lone pair of electron, the bonding electron will return to close the ring, and that is the ring there. Now the methyl group family attaches itself. Now this and the hydrogen ion will give this, and the catalyst is regenerated, and that's what we call methyl benzene. You can summarize these in this way. You can summarize it in this way. Generation of the catalysts. You can summarize it. Okay, the first step is you must generate the catalyst by this. Step one, you can put it just in this way. If you can't do that in the exam, the only way you can do this is by using this. You can use this by saying that it is a CH3 Cl. Yeah, that will forms a bond with aluminum. Forms a bond with aluminum chloride. Yeah, and that will result in formation of H3C plus what? AlCl4. That is one mark, but you must show the charges. You must show the charges that this is positive and this is negative, and you must show that this goes here. You must show those charges like that. That this is you must show this one as I've outlined here. The first step. Then the second step will be. You can summarize it as this. You can say this nucleophilic attack. Yes, to give this. Yeah, CH3. Now finally to give this. You can now use this and say there's an attack here. Let me use green. User one, I can say it is the catalyst is still there. that one. Then you show that it goes to the system. Then the catalyst is still there. Then you show this, then plus. That's all. Generation of the catalyst, generation of the electrophile, step number 1. Generation of the catalyst, that is step number 1. Then step number 2, nucleophilic attack, electrophilic attack. Generation of the electrophile, step number 1. Step number 2, electrophilic attack. This is step number 1. Step number 2, electrophilic attack. The electrophile now attracted to the ring. Distortion of the ring. Hydrogen expelled. This is formed. So if you can write these steps, you'll be okay. You are asked for, you can. These are the steps that are recommended for the purpose of revision. That was why I had to give you step 1, generation of the carbocation electrophile from the chlorine. Then electrophile attack the ring and distorting the ring. Then step number 3, ion, the hydrogen ion is expelled from the ring by this, and that is the generation. That is why I had to give this step. I gave all these for the purpose of revision. But the outline are just the 3 steps. Generate the electrophile, electrophilic attack, then hydrogen ion is expelled, restoration of the ring, formation of methyl benzene. Okay, now to E part of it. The E part of it says, the E part of it, 2-aminopropanoic acid is amphoteric. Write equation to show the reaction of 2-aminopropanoic acid with nitric acid. Okay, and I have to wipe this off. Okay. Excuse me, let me just clear this off. Okay, again, let's go. E part of it says 2-aminopropanoic acid is amphoteric in nature. Write chemical equation to show the reaction of 2-aminopropanoic acid with a nitric acid. Okay, you know, aminopropanoic acid has 2 groups: the the amino group and the carboxylate group. Okay, what we are going to do here is, the way you can write the equation is, there are 2 ways you can write the equation here. 1, you can write it like this. This is NH, okay, a nitric acid. With nitric acid, there's aqueous. With nitric acid, we have NH2. We will have a C, hydrogen, and a CH3, and that is, yeah. If you react with an acid plus acid, that is nitric acid. Nitric acid. Remember, the acid is a proton donor. The acid is a proton donor. Is going to release hydrogen ion here. So our product for this reaction will be a salt is formed. When you react with an acid, it will be H3N CH3 CH3. So now remember that it is a salt that is being formed. It is a salt that is being formed. So NO3, the charges, we have NO3 minus, and the charge here, because this one, because of the lone pair of electron that was here, I know that an amine, their basicity is as a result of the presence of the lone pair on the nitrogen. So when this dissociates, when the acid will dissociate, it will produce a proton. An acid is a proton donor. This proton or the hydrogen ion will leave and will be attached here, will bond here. There will be a coordinate bond that will be formed here. This amine group will donate a lone pair of electron here, and that is why it is formed here. There is a positive sign here, and that will be the equation. Another alternative of writing it is you could write it in this other way. You could write it like this. Oh, remember remember that in a neutral solution, this is how this group exists. The group exists like this. We have hydrogen, you can say OO minus, yeah, H3. Okay, this group here, because of this nature, because of this charge here, and because of this other charge here, this is a group. So this group like this, it is neutral because the amine group and the acid group, they have charges. The charges are, there's no charge that is dominant over the other one. And in this case, we call this situation a Zwitter ion. It's a Zwitter ion because it carries two charges, and the charges are equal. They cancel each other, and as they interact with themselves, it makes this compound to be neutral because these two charges, there's no one that overcomes the other one. All have the same level. And in that case, we call it a Zwitter ion. So reacting with an acid this time around, see what will happen. If it is reacting with an acid is this, which if it is reacting with an acid, this is an acid. If it is reacting with an acid, this will be the product. If it is reacting with an acid, the product will be H3 N plus remember an acid, this is an acid. This is an acid. Now, if an acid is added into this solution here, what happens? In order to remove the hydrogen ion, from the solution, what happened? The acid part, the carboxylate part of it with a negative charge, it has a lone pair of electron here. It has a lone pair of electron here. The lone pair of electron will be donated to this one, and this acid is, the undissociated acid is formed. If you were going to add a proton, if you were going to add an OH, An OH will do what? An OH, this amine group will donate a hydrogen, here, and it will react with an OH to form water. But since it is an acid here, what happens? The acid will be removed in the solution by doing what? By attaching itself to the lone pair of electron here, and the undissociated acid is reformed back. Okay, reaction with B, reaction with OH, B. You were reacting with OH, this will be the reaction with sodium hydroxide. With sodium hydroxide, this is what you will see. You can write it like this. With sodium hydroxide, you can write it as NH2, hydrogen, plus sodium hydroxide. Remember, this is a proton bases. Bases are proton acceptors. Bases are proton acceptors. Unlike in this other case, we said acid are proton donors. Here, they are proton acceptor. Why do we say bases are proton acceptor? They have a lone pair of electron on the oxygen here. They have a lone pair of electron on the oxygen. The lone pair of electron on this oxygen, the lone pair of electron on this oxygen will be used by when the hydrogen ion comes, it will be used as to attach to bond with the oxygen. The lone pair will be donated. We said the basis because of the lone pair of electron. The lone pair of electron will be donated to the hydrogen ion in forming water. So this will be our reaction. Here, we will have this. When a base reacts with an acid, a salt is formed again. So what is going to happen here? Salt and water is formed. So what is happening here is we will still have our NH2, CH3, and here the hydrogen here will leave. There's going to dissociation. The hydrogen here will leave and attach itself here, and the molecule of water is formed. So the sodium will come here. It will be a COO, Na. Then the hydrogen here will leave and combine here to form a molecule of water. You can either write it like this, you can write it in this form, or you can use this other method using the Zwitter ion method. Using the Zwitter ion with two charges, you can say H, the Zwitter ion like the one we did here. This is how you are going to write it. You will say it is N H3 N 2 carbon here. The charges are like the same way we wrote it here like this. That is the same thing. Now, if you now add a base from sodium hydroxide plus a base, this is a base from sodium hydroxide, the result will be what? Now, you have added a base here. What happened is that bases are proton acceptors. Bases are proton acceptors. So in that case, the proton here, or the hydrogen ion here will do what? We will be donated here to the lone pair of electron here, because there is a lone pair of electron here. There is a lone pair of electron here. So the lone pair of this here will donate a lone pair of electron, and this will be the result. When it donates the proton, and amine, the amine group is reformed. The amine group is reformed. We will have this. Amine group is reformed, and it will be a COO, a minus, a plus, so you could either, there are two ways you can write it. You can use the Zwitter ion method. Now here, because this is a stable, this is a neutral solution. I said it's a neutral solution irrespective of the ions. The ions, there's no ion here, they cancel out each other, because there's no ion here that is, there's no charge here. The charges are the same. The charges are the same. There's no one that is dominant, that has dominant over the other one. So for that reason, they are all, when they interact with each other, they become neutral. The solution is in a neutral condition. It is in a neutral condition. So when a base is added here, what happens? The base is removed from the solution by what? By this donating a proton, and that proton will attach itself to the lone pair of electron here. Since bases are proton acceptors, when they accept the hydrogen, or the hydrogen ion or the proton, it will result in water, and this is water, and that is, it returns back. In the same case, if it was an acid, this is a neutral condition. If an acid is added, to remove this in system, what happens? It will have to attach itself to the acid group here, and the acid is reformed. So reaction with acid, you can write this, or you write this. Then reaction with base, you can write this, or you write this other one down. That is how you can write this. It takes us to the last section of the question that says, give the structure and the general formula and the general name for 2-aminopropanoic acid when in a neutral solution, a pH 7. I said in a neutral solution, it has the ions there. So now, in this case, let me create space here. Okay. Now, give the structure and the general name for aminopropanoic acid when in a neutral solution. Okay, in a neutral solution, this is the structure. In a neutral solution, name, structure. You can either write this NH, you can either write this NH2, CH, the structure, you can write this one, or you can still write, you can write but this one. You can write this in as a Zwitter ion. This is a neutral solution. Structure and name of 2-aminopropanoic acids in a neutral solution. This is it. And the name, the common name that is usually given based on the answer, give the structure and general name of these amino acid. So this is the structure and the general name that we usually call this. You can call it alanine. Alanine, it has one. Then glycine has just one carbon. Alanine has two. So the name of this, we can call it alanine. The name is alanine. Name of amino acid, alanine. You can say it is alanine. Alanine. That is 2-amino acetic acids. Alanine. That is the general name is alanine, or 2-amino acetic acid. Alanine is the general name that we usually call it. Now, so this is a structure. You can either write this. This structure is a neutral. In a neutral condition. I said these ions will cancel out each other because the charges, there's no one that is more than the other one. So it is a result in a neutral condition. You can either write it using a zeta ion or you can write it using this. And the name of this compound, we call it alanine. Now, we said the next question is, draw the stereoisomer of 2-aminopropanoic acid. Okay, if you look at it critically, this compound here, and this one, here, we can put this asterisk here. You can put asterisk here because this compound has 4 different groups attached to the central carbon atom. We call it a chiral carbon atom because it has 4 different groups. This is an amine group, this is a methyl group, this is the hydrogen group, and this is a carboxylic acid group. So there are 4 different groups there. And we can write a stereoisomerism result from compounds that can rotate the plane of polarized light. And those type of compounds are compounds that have 4 different groups attached to the central carbon atom. And they can rotate the plane of polarization. For that purpose, the structure, the stereoisomer of alanine will be this one. Stereoisomer of alanine, using the structure, the first structure, using the first structure, we can, so the stereoisomer of alanine should be this. We will have hydrogen here. We will have hydrogen here. Hydrogen is bonded to the central carbon. Hydrogen is bonded to the central carbon. Now we have the amine group here. The amine group is this one. It can come here like this as let me say H2, H2N. Then this other one here, it can come here as you can put this as the methyl group, which is there. Then we will have this one here like something here. This is the acid group. This is the acid group here, which will be something like this. Now, since we say it rotates the plane of polarization, let's say this is our plane mirror here. That's our plane mirror there. So what we can have here will be, we will have our carbon here. we will have this one here like this. To be like, let me say it is H, O, O, C. We will have another one here, this other bond here on this side to be here. Then this other bond here, we will have it here as a CH3, and we will have our hydrogen here as usual. We have our hydrogen there. So we can now say this is a stereoisomer of alanine. Stereoisomer of alanine. Stereoisomer of alanine. A stereoisomer of alanine, this is how it's going to look like. That is how a stereoisomer of alanine is going to look like. By drawing this, we have a stereoisomer of alanine. And if you do that, you will have 5 marks. All these, you will have 5 marks. So, thank you. Once more, your synthetic routes, you should be very careful. You should know the reagent, the reaction condition, study it very well. And for your reaction mechanism conversion to methyl benzene, I said the first stage was generation of the electrophile carbocation electrophile, then nucleophilic amine electrophilic attack, then finally removal of hydrogen from the system, a hydrogen ion, and the regeneration of the catalyst, and the hydrogen chloride formed. And the last one, you can write reaction of zwitter ion, as I mentioned the other time. You can use the zwitter ion. And the stereoisomer, the name of the 2-hydroxy, 2-aminopropanoic acid. The name of 2-aminopropanoic acid is this one. It can remember, amino acid will exist in a zwitter ion form. That is, they carry 2 charges, the negative charge on the acid group and the positive charge on the amine group. And this makes this neutral because of that, and they interact among themselves. So then finally, using the structure of 2-amino propanoic acid, we can give rise to what we call a stereoisomer. And I said, once more, I said there is a stereoisomer there because there is a chiral carbon atom there. There's a chiral carbon atom there, a carbon atom containing 4 different groups or 4 different groups attached to the central carbon atom. This makes the compound gives the compound optical activity. It can rotate the plane of polarization. So this is the structure of it, and we said the common name for this acid is alanine. Alanine is the common name for it. So thank you very much for watching. Thank you very much for watching. We are still going to be discussing more of the questions. This is organic chemistry. We'll be going to inorganic chemistry. I wish you all the best in your exams. Once more, if you haven't subscribed to our channel, please motivate us to continue assisting you so that you can better prepare for your exam by liking, making comments, and most importantly, subscribing to our channel. Thank you very much. Wishing you best of luck in your exam once more.